All right, now that we touched base on how to represent vectors, how we can find the direction and magnitude, let's actually start combining vectors. So some operations we can do with vectors. We can subtract vectors, we can add vectors, we can multiply vectors by scalars, so like multiplying them by 2, 3s. You can also multiply vectors together. That will be covered in the next lesson. But one thing we're going to focus on is adding two vectors. So this diagram that's given right here is a visual of how you could figure out when you add two vectors. I'm not going to ask you for a visual, but sometimes it's nice to see it. So if you have this vector v, and then you have this other vector w, one way you can find what the addition of these two vectors are visually. Let me also say something else. This thing right here, when you add two vectors together, this is also known as your resultant vector. So what you can do is you can take your vector, your vector v, here's your initial point, here's your terminal point. When you want to add two vectors, you can pick up that vector w and put your initial point on top of that terminal point of your first vector, and then draw it how it was given. And then what happens is this, when I connect my initial to my terminal, the other one, that gives me the addition of those two vectors. So another thing we could have done, okay, is we could have just seen what this vector is, v. Okay, well, that in component form would be, I went 1, 2, 3, 4. So I went 4 to the right. Then I'm here, I just went up 1. So that's one vector. My vector w here is, okay, I went 1, 2, 3 to the right. And then I went 1, 2, 3 to up, so it's positive. Now, if I wasn't doing this visually, I am allowed to just add these two things together. So if I wanted to do v plus w, well, it's just, well, let me just be more accurate. 4 plus 3, and then it's 1 plus 3. So I get 7, 4. That would represent the addition of those two vectors. Another term for that is the resultant vector. So let's make sure that's accurate. I'm going to get rid of this so I can follow. Okay, so if I start here, so I'm going to look at, to be clear, I'm trying to get the component form of that black vector, v plus w. Well, it looks like I went over 1, 2, 3, 4, 5, 6, 7, looking good so far. And then I went up 1, 2, 3, 4. So again, we most likely will be doing it just algebraically, but visually, that is also how it works. So let's continue in example 3, doing some operations with vectors. So here's a visual for your vector u and your vector v. So write u and v in component form. So it's going to be very similar to what we just did. All right, well, u in component form and then v in component form. So I started my initial and I went 1, 2, positive 2, and then I went 1, 2, 3, 4. Okay, now for v, I went 1, 2, but then I went down 2. So that's why it would be 2 and then negative 2. Now, just like we talked about, this is known as always your resultant vector, your u plus v. But what we can do is we can just add them algebraically as well. So let's change colors. U plus v equals, well, what's 2 plus 2, comma 4 plus negative 2. We end up getting 4, 2. And once again, if we compare it to that visual, we have 1, 2, 3, 4, and then up 2. So good. So I didn't give you a visual for subtraction or for something that looks like D, but we can just do it algebraically. U minus B. Well, I'm going to take away my x's, so 2 minus 2, comma, 4 minus negative 2. So that becomes a plus. So we end up getting 0, 6. So when you subtract these two vectors, this would be your vector component form. So the other operation we can do is I can multiply. So I'm going to do this step by step. I can multiply my vector u by a scalar of 2. So what this is saying is 2 times your component form for u, which is 2, 4. So that gives me 4, 8. So that just means you're making this vector twice as long, right? Now let's use a different color, 3b. All right, well now I'm going to make my vector v 3 times as long. Save me some space, so I'm going to go this way. So I end up getting 6, negative 6. Whoops, sorry. All right, but the last step is we actually want to subtract these two things we found. So 2u minus 3v. Well, that equals 4 minus 6. Because again, I already found this stuff, so I'm just doing 4 minus 6. And then 8 minus the negative 6. So we end up getting negative 2. And then 8 plus 6 is 14. All right, one other thing we're going to find in this video is E is giving me this notation. So we briefly showed it to you earlier. Remember, this is your notation to find your magnitude. Well, we already know what U plus B is. We found that in B. So we're actually finding the magnitude of this component. This vector in component form. Now, if you're someone that has to rely on a visual, that is a-okay. You know, you can just figure out what this is. This is 1, 2, 3, 4, and then up 2. So if I wanted to just do this, that's totally fine because that's still the same component form, right? This is actually known as a vector in standard position because your initial point is on your origin. Well, again, if you needed that visual, remember this is 4, this is 2, you can find that length of that vector, the magnitude, by doing Pythagorean theorem. But I'm hoping you get okay with, since we've been working with this all term, this is just the square root of 4 squared plus 2 squared. And that's just from Pythagorean theorem. So we end up getting the square root of 16 plus 4. So we get 20. And you're going to pay attention to instructions. I'm going to have us go ahead and simplify this so we keep getting better and better at that. So that becomes 2 root 5. That is your magnitude for your resultant vector. In other words, you found the length of this vector, right? The R, the hypotenuse, all those lovely things.